We're going to continue with reaction stoichiometry. We've done some mole to mole conversions where you start off with the moles of one substance and found the moles of a different substance in a reaction. We did a mass couple of problems where you started off with the mass of one substance in a reaction and found the mass of another substance in the reaction. But remember, there's other relationships we've had with moles. So we know that 1 mole of a gas or a substance at standard temperature and pressure is going to be equal to 22.4 liters. So that's one conversion we've used. We also know that we can go to molecules or atoms of its elements by using Avogadro's numbers. So we're going to look at those two examples, and then we're going to look at some where you might start off with a mass and go to a volume or something along those lines. So this particular problem, we're doing a volume problem. It's telling us that we have hydrogen reacting with nitrogen to produce ammonia. So this is a reaction we have already done, so I'm going to go ahead and quickly balance this one. So we need our coefficient. So again, you're looking for the volume of hydrogen. So unless they tell you otherwise, look for liters. If you have 5 liters of nitrogen. So again, I'm starting off with nitrogen and I want to go to hydrogen. So in order to get from one of these to the other, I've got to use my mole ratio. So in this particular problem, I'm going to start off with liters. I want to go to moles. This is going to be of nitrogen. So I have my 5 liters of nitrogen. I know that in 1 mole of nitrogen at standard conditions, there would be 22.4 liters of nitrogen. That's one of our conversion factors that we've learned in the past. That'll get rid of liters of nitrogen. The middle step, remember, is our mole ratio, where we're going moles to moles. This is why we need our balanced equation, so we can see that we have 3 moles of hydrogen reacting with 1 mole of nitrogen. Since I'm in moles of nitrogen, I want to put my 1 mole down here. I want to put my 3 moles of hydrogen up here because that's what I'm looking for. And then finally, we're going back to volume. So we would take our moles back to liters. And in this case, we know that 1 mole of hydrogen at standard conditions is 22.4 liters. And then the rest, of course, is just doing the math. So if you look here, you can see that 24.4 is on the bottom, 24.4 is on the bottom here. That would cancel. So I'd end up with 15 liters of hydrogen. 5 times the 3. So let's look at one more volume. Okay, maybe I don't have one more volume. There it is. All right, so here's our equation. It's already balanced. If you look at this equation, you should recognize this as a combustion reaction. So we have a organic compound reacting with hydrogen to produce carbon dioxide and water. It just happens to already be balanced. It tells us that we have 20 liters of oxygen, so we have 20 of these. And it says how many liters of carbon dioxide are produced. Okay, so we're going to start off with our 20 liters of oxygen and convert it into moles. So again, liters to moles. We know that 1 mole of oxygen will go to 22.4 liters of oxygen if we're at standard temperature and pressure. So we're assuming that. So liters of oxygen will cancel. I'll be in moles of oxygen. The next step is going to be my mole ratio. So I want to go moles to moles. So I have 5 moles of oxygen to 3 moles of carbon dioxide. Since the moles of oxygen is on top here, I need to put the oxygen on the bottom. So the 5 moles will go here. Put what I'm looking for, which is the carbon dioxide, on the top. And that's our 3 moles. So I'm getting these numbers from my balanced equation to get my mole ratio. Moles of oxygen will cancel, and the last step will be taking my moles now of my new substance, which is carbon dioxide, to liters of carbon dioxide. So I know my 1 mole is going on the bottom, my liters on the top. That's my conversion factor is 22.4 liters. Moles of carbon dioxide will cancel. And then, of course, the rest is doing the math. So I've got my 20. And again, you don't have to show all this work, but 20 would be divided by 22.4, then times 3, divided by 5, and then times 22.4. So you're going to end up getting 12 liters of CO2. So let's look at a problem where you are starting off with one kind of a substance, one kind of a material of the substance. So this time we have 25 grams or a mass of a substance, and we're looking for the volume of a different substance. You're still going to use the same processes. You're just going to use different conversion factors because we have masses going to moles and we're going to have volumes going to moles. So in this case, let's go ahead and write our reaction. So we have nitrogen reacting with hydrogen to produce our ammonia. So we already know this equation. It's telling us we're looking for the volume. So we're looking for X liters of ammonia if we have 25 grams of nitrogen. So whatever you start with, in this case we're starting off with grams, you take that to moles. If it had been liters, you take it to moles. If it had been molecules, you take it to moles. All right. So in this case, it was grams, so we'll take the mass of the nitrogen. We have 25 grams of nitrogen. We know 1 mole of nitrogen is going to be equal to its gram formula mass. So nitrogen has 14 times 2, which will be 28, will be its gram formula mass. So we'll cancel out our grams of nitrogen. Our next step is our mole ratio. So we'll take our moles of nitrogen, of which we have 1 here, and go to our moles of ammonia, of which we have 2 from our coefficients. So since moles of nitrogen is on top here, it needs to go on bottom here. So this 1 came from here. And then my moles of ammonia, of which will be 2. This 2 comes from this 2, from the balance equation. Moles of nitrogen cancel. So if I solved at this point, I'd be in moles of ammonia. They are asking me for volume of ammonia, so now I want to take the moles of ammonia to liters. So to do that, I'm going to say I have 1 mole of ammonia. The conversion factor between moles and liters is 22.4. So that's going to go on the top. Moles of ammonia cancel, and now the rest is just doing the math. So I'd have my 25 divided by my 28 times 2 divided by 1 times 22.4 divided by 1, and I should get 40 liters of ammonia. So let's look at this problem. This again was one of our reactions we did earlier, so I'm going to go ahead and write down the balanced equation real quick. It says we have 5 grams of potassium chlorate decomposing to potassium chloride and oxygen. What is our volume of oxygen at STP? So this is going to be just like the last one we did. We're starting off with grams. We want to go to moles. So we take our 5 grams of our potassium chlorate. We know 1 mole of potassium chlorate is equal to its gram formula mass, and we figured that out to be 122.5 earlier. So remember, potassium's 39, chlorine's 35.5, oxygen's 16 times 3, which is 48. You add 39, 35.5, and 48, and you should get this value. Grams of potassium chlorate will cancel. I'll be in moles of potassium chlorate. My middle step, remember, is always my mole ratio. What that does is it allows me to go from what I start with, which is my potassium chlorate, to my oxygen, which is what I'm looking for. So I'm going to use my balanced equation coefficients to do that. So this is telling me 2 moles of potassium chlorate produce 3 moles of oxygen. I'll put my 2 moles of the potassium chlorate down here at the bottom. So that will cancel. my 3 moles of oxygen on the top so I can get to what I'm looking for. And then finally, I want to go moles to liters. We know 1 mole of anything at standard temperature and pressure is 22.4 liters. So that's the conversion factor I use here. And now the rest is plugging in your calculator. So I'd have my 5 divided by 122.5 times 3 divided by 2 times 22.4. And I'm getting 1.37 liters of oxygen. Now this one's a little different because it's asking us for molecules instead of liters. We already have our balanced equation, so it says how many molecules of water, so I'm looking for X molecules of water, I'm going to use MC for molecules, are produced if you have 2 grams of sodium sulfate produced, so 2 grams of sodium sulfate. So I'm going to start off with the 2 grams of sodium sulfate. So, as before, we want to get our grams to moles. Whatever you start with, take it to moles. So we know 1 mole of sodium sulfate is equal to its gram formula mass. So we'll have to calculate that. So we have 2 sodiums, so 2 sodiums is 23 or 46. We have 1 sulfur, which is 32. We have 4 oxygens, each is 16, which is 64. So 46 plus 32 plus 64, I'm getting 142. Make sure I did that right. 46 plus 32, 64. All right, that goes here. Grams of this will cancel. Now, just like before, we're going to now go moles of what we started with, in this case the sodium sulfate, to moles of what we're looking for. In this case, that's going to be water. So now we are going to use our coefficients from our balanced equation. And I think this is wrong. There should be a 2 here. All right. So if I'm balancing that right, that'd be 2. It'd be 2 before. That's right. All right, so that was missing, so that 2 should have been there. All right, so now I have my coefficient. So I'll have 1 mole of my sodium sulfate down here at the bottom, so that the moles of sodium sulfate could cancel. 2 moles of water on the top, so that I'll be in the substance I'm looking for. These are coming again from here. Okay. Then finally, we want to go moles of what we're looking for, in this case to molecules. So I'll put my mole on the bottom. And remember, the relationship between moles and molecules is Avogadro's number, which is 6.02 times 10 to the 23. Moles will cancel. And now the rest is just putting everything in your calculator. So 2 divided by 142 times 2, and then times 6.02. If you're doing this on your calculator, it'll be 6.02, then EE or EXP button, 23, and then equal. And I'm getting 1.70 times 10 to the 22 molecules of water. Remember units and formulas.